People of shockwaves. Percy Bridgman, the Dean of High-Pressure Physics. In 1909, a young physicist at Harvard was struggling with a frustrating problem. Every apparatus he built to study materials under high pressure leaked. No matter how carefully he designed his seals, the pressure forced its way out. Then came a moment he would later describe as having a strong element of accident, a serendipitous insight that revolutionized high-pressure physics. He invented a seal that tightened itself under pressure, turning the force working against him into his greatest advantage. This invention opened a new realm of physics and would eventually earn him the Nobel Prize. This is a story of Percy Bridgman, the Dean of Static High-Pressure Physics, whose data became essential for understanding shock compression. Percy Bridgman was born in 1882 in Cambridge, Massachusetts, the son of Raymond Landon Bridgman, a newspaperman and author. He received his early education in public schools in the nearby city of Newton until 1900, when he entered Harvard University. Bridgman studied physics at Harvard College and remained there his entire career, M.A. in 1905, Ph.D. in 1908, physics instructor in 1910, assistant professor in 1919, Hollis Professor of Mathematics and Natural Philosophy in 1926, Higgins University Professor in 1950, and Professor Emeritus in 1954. Harvard was his scientific home for 54 years. In 1905, Bridgman commenced his high-pressure studies, which he continued throughout his whole career. He focused his researches on the effects of static high pressures on materials and their thermodynamic behavior. The technical challenge was immense. How do you contain extreme pressure without leakage? His essential invention came in 1909, the self-sealing feature of his first high-pressure packing, the so-called Bridgman unsupported area seal. The genius was in the geometry. He designed the seal so that higher pressure forced it more tightly against the sealing surface. The very force trying to escape actually improved the seal. This eminent discovery pioneered the field of high-pressure physics. It was, in Bridgman's own words, a strong element of accident. Using initially a screw compressor from 1908 to 1909, which allowed maximum pressures up to 6 kilobars, he succeeded in pushing pressures up to 20 kilobars by employing a hydraulic press in 1910. Further technical improvements allowed gradual pressure increases up to 30 kilobars, facilitating the first routine measurements of the mechanical, electrical, and thermal properties of matter under extreme compression. Still higher pressures, up to about 400 kilobars using his so-called Bridgman opposed anvil apparatus, were finally obtained in quasi-fluid systems in 1930. He found that all liquids, with the exception of water, behave qualitatively alike, the viscosity increasing with pressure at a rapidly increasing rate. Subjecting water to high pressure, he found new crystalline forms. 1. Produce above 40,000 bars, was the so-called hot ice with a melting point of about 200 degrees Celsius, ice that remained solid at boiling water temperatures. In 1932, he took an active part in initiating a program at Harvard for high-pressure studies devoted to geophysical behavior. One of Bridgman's most famous undergraduate students was J. Robert Oppenheimer, who later became scientific director of the Manhattan Project. During World War II, Bridgman participated in the Manhattan Project and measured the static compressibility of uranium and plutonium, critical data for nuclear weapon design. He also studied the plastic flow of steel under high pressure as related to the strengthening of armor plate. He developed a method for increasing the yield point of artillery gun barrels by preliminary stretching with internal hydrostatic pressure, which remains standard practice today. Although he never studied the behavior of matter under shock compression himself, his numerous papers on high-pressure research and his famous textbook, The Physics of High Pressures, published in 1931, have become standard sources of reference for shock physicists as well. His carefully measured data on static compression and on the state of matter, such as polymorphism and phase transitions, were often the only available source of information when physicists and military engineers began to investigate the behavior of solids and liquids under shock loading. He first suggested the use of the pitot-resistive effect to measure static pressures and applied manganese wires in 1950, a method which was resumed later in solid-state shock physics experiments. Bridgman won the 1946 Nobel Prize for Physics for the invention of an apparatus to produce extremely high pressures and the discoveries he made therewith in the field of high-pressure physics. In the early 1950s, he performed experiments on the compressibility of glass up to static pressures of 200 kilobars, approximately the upper limit accessible with his anvil compression technique. His writings on high-pressure physics, spanning 1909 to 1963, combine experimental expertise with philosophic insight. He is renowned not only for his contributions to static high-pressure research, but also for his brilliant mechanical constructions. In his book Dimensional Analysis, published in 1931, he treated mathematically the Buckingham Pi theorem from 1914 to 1915, which has become the basis of most dimensional analyses in engineering dynamics. Bridgman was a member of the National Academy of Sciences and received numerous awards: the Rumford Medal in 1917, the Crescent Medal in 1932, the Roosboom Medal in 1933, the Comstock Prize, the Research Corporation Award in 1937, and the Bingham Medal in 1951. Since 1977, the Bridgman Award of Air-Apt is given biennially to researchers who make significant contributions to high-pressure physics. A crater on the far side of the moon is named for him. Percy Williams Bridgman died in 1961. Though he never fired an explosive or created a shock wave, his static high-pressure data provided the essential baseline for understanding dynamic compression. Every shock wave experiment that compares dynamic to static compression stands on Bridgman's foundation. From an accidental insight to the Nobel Prize, Bridgman showed that extreme pressures reveal new states of matter. Percy Williams Bridgman, the physicist who squeezed matter until it revealed its secrets.